Project 6, where we'll be learning about trigonometry. The first formula we're going to deal with is called the arc length formula. And unlike most formulas that are written solve for one variable, this is set up as a proportion. It says that the ratio of the central angle to the 360 degrees of a circle is equal to the ratio of the arc length compared to the 2 pi r circumference of the circle. So let's get some practice with this formula. We're trying to find the length of this arc right here, PQ. We'll call that length L. What we want to know is the central angle of this arc, which is 60 degrees. So we'll plug that into the formula. And the one other thing that we need to know to use this formula is the radius, which in this case is 9. So we'll plug that in as well. Now this formula reads 60 over 360 equals L over 18 pi. Next I'll multiply both sides by 18 pi to get rid of the 18 pi on the bottom. Now I have L equals 1080 pi over 360, or 3 pi, which we can turn into an approximate answer of 9.4. And that's our arc length for this particular arc. The next thing we want to talk about is trigonometry. Remember basic right triangle trig. For a given angle within a right triangle, the sine equals the opposite over the hypotenuse, the cosine equals the adjacent over the hypotenuse, and the tangent equals the opposite over the adjacent. This can be summed up using the acronym SOHCAHTOA. We're going to use these ratios in reverse sometimes, using what's called inverse trig, and we're also going to need to know the Pythagorean theorem that says a squared plus b squared equals c squared, where c is the hypotenuse side. Alright, so let's put this knowledge of trig to use and solve a right triangle. What that means is we have to find any unknown angles and sides. The information we're given here at the start is a known angle and a known side. We can use this information to go and find one or more of the other sides. To find this side B, we can use the fact that we know the angle. Across from the 90-degree angle, we know the hypotenuse. And opposite our angle, we want to know the opposite side. So with two knowns and one unknown, we can use one of our trig ratios. Since we're dealing with opposite and hypotenuse, we'll be using sine. The sine of our 60-degree angle equals the opposite b over the hypotenuse 11. By multiplying both sides by 11, we know that b equals 11 sine 60. We can use our calculator to figure out what this would be as a decimal, and we get 9.53. Now that we know 9.53 is b, what are we still missing? Another thing we're missing is angle A. Well, this one's going to be easy to figure out. The three angles of a triangle should add up to 180. We already know we have a 60-degree angle, and we also know we have a 90-degree angle. So if we subtract those 150 degrees from 180, we end up seeing that A equals 30 degrees. And we can put that on the triangle. Now the last thing we're missing is this side, little a. You could do this using Pythagorean theorem and the two sides that we already know, but you always want to try to use things that were given at the beginning of the problem. So I'd really like to use this 60-degree angle again, and I'd really like to use this 11 side. Well, if we're thinking about the 60-degree angle, this makes A the adjacent side, and 11 is still the hypotenuse side. If we're dealing with A and H, adjacent and hypotenuse, we're dealing with cosine. The cosine of our 60-degree angle equals the adjacent A over the hypotenuse 11, which, similar to the sine problem up above, ends up being A equals 11 cosine 60, which my calculator tells me is 5.5. And we can throw that on the triangle, and now we've solved all the missing pieces of information, and this problem is done. Let's do this again for a problem where we weren't given an angle. This time we're given two known sides. Let's go try to find one of the missing angles, A or B. I'll start looking at angle A. If we're thinking about angle A, that makes 4.4 the opposite side, and it makes 11, and because 11's across from the right angle, that's the hypotenuse side. Since we're dealing with O and H, this would be sine. So the sine of A equals the opposite over the hypotenuse, or 4.4 divided by 11. This is where we're going to need inverse trig. If we inverse sine both sides, we get A equals the inverse sine of 4.4 divided by 11. Make sure your calculators are in degree mode here, and we get an answer of 23.6 degrees. We'll throw that in, And now to find the missing angle, I don't really mind using this angle that we just calculated. So again, I'm going to use the knowledge that the three angles add up to 180 degrees. So this missing angle B should equal 180 minus the 23.6 and 90 degree angles we already know are in the triangle. And that ends up getting us 66.4 degrees. Now finally, we're missing one more side, side little b, and when we're after a side, I really like to use the known information, which in this case is the 11 and the 4.4. Now we won't use trig here, but instead we'll use the Pythagorean theorem. This says a squared plus b squared equals c squared. So 4.4 squared plus b squared equals 11 squared. And I'm going to keep things exact as long as I can, so I'm going to move over that 4.4 squared and then square root both sides. And I'll just type that whole thing into the calculator. And that gives me 10.08, which was our final piece of missing information. Alright, so now we're going to do a more advanced example that's going to require us to look at two different triangles in one picture. The first triangle we're going to look at is the little triangle with the 50-degree angle. The other triangle we're going to look at is the big triangle with the 41-degree angle. In the little triangle, we have a 50-degree angle, and the two variables we're trying to solve for, h and x, are the opposite and adjacent sides of that little triangle. Well, when we know opposite and adjacent, we're going to use tangent. So the tangent of that 50-degree angle would equal the opposite h over the adjacent x. Let's try to solve this for one variable, h, by multiplying both sides by x. This gives us h equals x tan 50. And that's as far as we can go in this triangle. Now let's look at the big triangle with a 41-degree angle, and h is still the opposite. However, if you look at the big side at the bottom of this triangle, it is equal to x plus 7, because it equals this segment plus this segment. So that x plus 7 is the adjacent side of the blue larger triangle. Now, since we're again dealing with opposite and adjacent, we're still dealing with tangent. The tangent of this 41-degree angle is equal to the opposite h over the adjacent x plus 7. And again, by multiplying by x plus 7 this time, I can solve for h. h equals x plus 7 tan 41. And now that I have two different equations equal to h, I can actually set them equal to each other to try to solve for x. And the way that I'm going to do that is by turning these tangents into decimals and then manipulating the equations. The tangent of 50 is 1.19, and the tangent of 41 is 0.87. Once I get those tans out of there, this problem looks a little bit easier. I can now distribute this 0.87 to get 1.19x equals 0.87x plus 6.09. Now I'll subtract the 0.87x to get the x terms on one side, and I get 0.32x equals 6.09, which I'll divide both sides by 0.32 now, and get a final x of 19.03. And now that I know what x is, I can plug it into either one of my h formulas up here to go and find h. I'll plug it into the easier one, which was the red one. And this gives me h equals 19.03 times tan 50, which my calculator tells me is 22.68. And while that was a little bit of a complicated problem, we now have our answers for x and h. In this last problem, we're going to deal with a circle that has a radius intersecting with a chord forming right angles. We're told that the chord is 18 millimeters long and the radius is 30 millimeters long. We're going to rely on a theorem from geometry that says that in a circle, a radius perpendicular, that means forming right angles, to a chord bisects the chord. Bisects means it cuts the chord in half. Well, if we know that the chord is 18 millimeters long, this means that it's going to form two 9-millimeter segments. Now, we know that the radius is 30 millimeters long, and a lot of people think that it's a double bisection, so this is going to be 15 and this is going to be 15, but that is not true. Where we can use our knowledge that the radius is 30 is here with this radius on the other side of the problem. Now, what you might be starting to notice is we have a right triangle right here that we can use to help us. One of the pieces of information we were supposed to find was the central angle y. Well, currently, looking at y, I see that 9 is the opposite side and 30 is the hypotenuse side. So I could use some right triangle trig and the sine of y to solve for y. So the sine of an angle is the opposite over the hypotenuse, so 9 over 30. And since it's the angle we don't know, we're going to use inverse trig. And y will equal the inverse sine of 9 over 30, which is 17.5. That was one of the two key pieces of information we were supposed to solve. Now the next thing I'm supposed to figure out is what x is. X is part of this 30 millimeter long radius, but it's not part of the triangle we've been starting to solve. But this segment right here is. Let's call that segment z. If I knew how long z was, I could subtract it from 30, which is the length of the entire radius, and that result would be x. To find z, I'm just going to use Pythagorean theorem for this triangle. Z squared plus 9 squared should equal 30 squared by the Pythagorean theorem. So z squared plus 81 should equal 900. Z squared equals 819, and by square rooting both sides, we get z equals 28.6. Now, as we just said, x is part of this 30 unit long or 30 millimeter long radius. And now that we know z, we can do x equals 30 minus that chunk, 28.6. And that gives us an answer of x equals 1.4 millimeters. And now we've solved for x and y, and there's nothing left to do on this problem. All right, so let's just wrap it up with a few key points. This lesson is all about trigonometry, which means we are looking for right triangles in these problems. Remember to use SOHCAHTOA. Sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. And lastly, remember that if you're trying to solve for the angle in a problem, you should be using inverse trig. If you're looking for a side, you should be using normal SOHCAHTOA. That's it for this lesson. If you came away with anything else, write it down now. Otherwise, see you next project.